This is a nice little theorem. If you want to see whether a homomorphism is one-to-one, you just need to look at the kernel. If the kernel is trivial, the only thing that maps to the identity in H is the identity in G, then it's one-to-one. Otherwise, it's not an if and only if statement. So suppose that means that whenever I have phi of x equal phi of y, then x has to equal y. So let x be in the kernel. Then phi of x is equal to the identity of H. That's the definition of the kernel. But that's equal to phi of E of G, because we know that the identity maps to the identity. So because we have two things being equal, phi of x and phi of EG, so here y is equal to E of G, we're going to conclude that x is equal to y, which equals to E of G. The thing that was in the kernel was the identity. So that's the only thing that can be in the kernel, and we get that the kernel equals the identity. All right, now suppose that the kernel equals just one element. By the way, this of course is improper. Kernel phi should be a set, so really it should be this. However, mathematicians are lazy, and if it's just a singleton, especially with the identity, we'll just sometimes write it like that. That's common, but it's technically incorrect. See what happens. I'm going to prove it's a one-to-one, so I'm going to assume that this is true, and I'm going to show that x equals y. Application. If you have phi of x equals phi of y, I can multiply on both sides by phi of y inverse. Phi of y inverse. And that tells me that phi of x, phi of y inverse equals the identity in H, because these just cancel each other out. Oh, but phi of y inverse is equal to phi of y inverse equals E of H. Oh, I can use the homomorphism property to get phi of xy inverse equals E of H. That's really what's going on there. This is in the kernel. But there's only one thing in the kernel. It's equal to that. And so if I multiply both sides on the right by y, I end up with x is equal to y. So it's one-to-one. And we're done.